About the oxidation reactions of alcohols. Now what we'll learn, and this sort of piece by piece, I'm going to build up gradually. What we need to know is that, first of all, remember what a primary, secondary and tertiary alcohol here is. So I'm going to remind you this is a primary alcohol because it's got one carbon attached to the carbon with the hydroxyl on it. I'm going to remind you as well that this is a secondary alcohol because the hydroxyl is attached to a carbon that's attached to two carbons. Okay, this is stuff that we've seen before. Tom's nodding, it's encouraging, right? So we've seen this before. And we also have learned that we can do these things called, get these things called tertiary alcohols as well, which behave a bit differently. And there, the hydroxyl is attached to a carbon that's got three carbons coming off it, so you end up with that. Okay. Now we're going to learn about the oxidation of these. Now when you show oxidation in chemistry, you know that oxidation's got actually four meanings in chemistry. The first of which is gain of oxygen, that you learned way back in year 8 or 9, sort of carbon turning into carbon dioxide, gain of oxygen. We've also learned this year that oxidation is, well, you did it last year as well, loss of electrons or gain of increase of oxidation number. But it's also loss of hydrogen. So oxidation is also loss of hydrogen. And we can, when I say hydrogen, I mean loss of H2. So this hydrogen and this hydrogen can be lost from a primary alcohol. So this is loss of H2. And what you end up with is a molecule where, again, carbon must form four bonds and oxygen must form two bonds. So it must be, if we're taking away this hydrogen and this hydrogen, it must be you draw a bond between, an extra bond between the carbon and the oxygen. Let's draw that now. And you end up with that. Okay. What's the name of that functional group? And what's the name of this homologous series, please? Tell each other. There's a nice frown on your face at the back, Lola, so we're going to ask you. It isn't aldehyde, because we've got that H next to this functional group. That functional group being what, Lola? Carbonyl, yeah, carbonyl. So good, if it's carbonyl, well done, is a C double bond O next to carbons and hydrogens. This is a carbonyl, specifically it's an aldehyde rather than a ketone, because it's got a hydrogen on one, at least on one side. Okay, so you get an aldehyde. So you might want to just remind yourself of that. Something that people forget, a little reminder while I'm at it, aldehydes are RCHO when you write them out in the condensed form. Worth remembering that if you've forgotten it. R being the rest of the molecule. There must be another product. This equation is not balanced, is it? So what must the other product here be if this oxygen is being used to take away these two hydrogens? What do you reckon it is, Lauren? If this oxygen is being used to take away these two hydrogens? It's water, yeah, good. So you generate water as well. And actually, secondary alcohols do exactly the same. Hopefully you're leaving plenty of space. If you're not, you're going to mess up your sheet. But secondary alcohols do exactly the same thing. So there's the hydrogen on the oxygen and hydrogen on the adjacent carbon are lost. What are we going to form then? What's the name of the product we form then, or the name of the products we form if we do that reaction in exactly the same way? Have a little think. Try and work it out. Lose that hydrogen, I'm going to lose that hydrogen. I'm going to form, it's going to be analogous to this one here. So any people want to guess? Millie's looking really confident, so we'll go with Millie. Right, hang on, so let's think about it. So why don't you draw all of this molecule without this hydrogen and without this hydrogen? Is that too small? Can you see that okay? Not quite. I'll just remind you what an ester is on a different bit of paper. An ester, remember, it's got a carbon, it's a bit like a carboxylic acid but with a carbon chain instead of the H for a carboxylic acid. So it's not an ester. So I've drawn the molecule, but I've taken away those two hydrogens. I need to make another bond, don't I? Where's the bond? What bond is missing? What bond do you need to add to this? Which atoms are not making enough bonds right now? Right? And thank you for the whisperer too, for that. Appreciate that. I quite like people to think under pressure, right? I think that's a good skill to have, right? So we're going to get that. So do you know what we call a molecule that looks like that? So again, it's a carbonyl, but it's not an aldehyde, so it must be a... It looks a little bit like a lock, I think. Ketone, here we go. And we get a byproduct of water again, exactly the same reason as before. And the tertiary alcohol doesn't oxidize. Can you see why not? No reaction. Why doesn't the tertiary alcohol oxidize? Take hands up on this one. If you don't think about it. Why can't this one react? Is that hand, are you moving? You've sort of got a confident look on your face.
You can't pull up the C in the middle that's attached to the O, you can't double bond.
Because
it's you take the hydrogen off of the...
Yeah, there's no hydrogen on here, exactly. There's no hydrogen on here to fall off, so you can't lose this very easily. There's no way of that happening. Okay, so yeah, so you can't have this same reaction because you haven't got the hydrogen on the adjacent carbon. Right, good. But stupidly, I've not left much space here, so I'm going to have to sort of fight this a little bit. But so what I'm going to do is I'm just going to carry this on down here a little bit. So I'm going to draw the aldehyde again. If you've got space, fine. If not, you're going to have to do it the same as me. But aldehydes are really easy to oxidize. And when you chuck in oxidizing agents, it's pretty hard to only add a little bit. You always tend to end up adding an excess. So you would generate an aldehyde, but the aldehyde's easy to oxidize. Now, oxidation is gain of oxygen. If I slide an oxygen into this molecule between the carbon and the hydrogen, which is what happens, I end up with... Whoops. I end up with this. What do we call that stuff? You've seen this in Mr. Craig's lessons as well. What do you call that, Scarlett? So what's the functional group? It's a carboxyl group, so this stuff is 2 carbons, so it's F. It's not ethanol, ethanol's up here. You just said it's a carboxyl, which by that you mean carboxylic acid, so it's ethanoic acid, right? Do you see how these things have to be learned? I'm not going to go in without a bit of practice. So, is that equation balanced, or do we need to add water again? Hands up for thumbs up for balanced, thumbs down for not balanced. Yeah, most of you spotted that that's balanced. So all we've done is kind of, it doesn't work like this, but this oxygen's kind of jumped in between that carbon and the hydrogen there. So overall, for the primary, we've really done this, haven't we? Done a 2-stage oxidation, which I'm going to spend a bit more time on. We've done this overall reaction, and you need to be able to write it out in this way as well. So we've got double oxidation all the way to a carboxylic acid and 1 molecule of water. Okay, that's what's gone on there. Happy with that? Makes sense? So we've got the carboxylic acid, it's gone via an aldehyde to a carboxylic acid. You generate 1 molecule of water in that overall process. You've got to be comfortable with that happening. Secondary alcohol can't be further oxidized, or the ketone can't be further oxidized, I should say. And the tertiary alcohol doesn't do anything.
Why is the oxygen squared up?
because it's not because we're not using O2, we're using an oxidizing agent, and I'm going to go into that level of detail in a second. So we're going to talk about what the oxidizing agent is. We're not going to get into much about what it's doing, but we're going to talk about a bit more about how we do the reaction. Okay. So that, if you just while we're doing it, by the way, you can represent reduction like that. So sometimes you see reduction like that. Okay, I'll come back to that another time. Just organic speak for oxidation and reduction. Organic chemists are lazy. Happy with that? Everyone okay? All right. So that's the first thing we've got to get our heads around and learn, I'm afraid. But we've got to think about how we do that reaction. So reagents and conditions. So reagent is a word that you'll find me using. I think I didn't really know what it meant until I was well into uni. People were using the word reagent. You don't know what reagent means? I didn't know the difference between reagent and reactant, but reagent is something that you basically get off the shelf. So you can go and see Mr. Corliss and he can give you a bottle of it. The reactant in this is actually a dichromate ion and hydrogen ions, which we'll see in a bit. They're the reacting species, but the reagent is the chemical you use off the shelf. So reagents, but really I might be talking about reactants there. So just a familiarity with words that you might hear me using to try to teach you properly as I'm going along. So how do we do this? So oxidation is performed. Oxidation is carried out by heating with it needs to be acidified. I'll explain why. It could be sodium or potassium dichromate 7. Why have I put the Roman numerals afterwards, do you think? Finish catching up with the writing and then tell me why it's dichromate 7 and not dichromate 3 or 9, or why do I need that 7 after it? David?
The oxidation number of it.
Oxidation of it, of what?
Of potassium dichromate.
Well, is it the oxidation number of the potassium?
Of the dichromate.
Of the 8 bit is referring to the oxygen.
Yeah.
So the chromium, I think is what you're saying. The oxidation number of the chromium in dichromate is 7. Yeah. The 8 bit, like permanganate, dichromate, nitrate, sulfate, it's telling you there's an oxygen, and that oxygen is always -2. But it's the oxidation number of the thing, the chromium there. Okay, it's called dichromate because there's 2 of them. And so we use hot potassium dichromate to oxidize these things. And while we're at it, we might as well do a little bit of revision of redox chemistry. We know how to balance half equations, don't we? So if I tell you that this stuff is orange, this will come up in a question I'm going to give you next week at some point. I'm expecting you to know that stuff is orange. And when you do the reaction, it gets reduced, because it's an oxidizing agent, right, to species which is green, chromium 3. Can you remember how to balance that half equation? If you can have a go at that yourselves, if you're completely stuck, just give me a dirty look and I'll give you a hand. Or cheat by copying someone near you. Got it? Tom? Oh, Tom's got a sad face. How many chromiums on the left, Tom? We've done it, Niraj. Right, if you finish it, I want people to think about it a minute. If you finished, can you do the half equation for the oxidation of the ethanol to ethanoic acid? The ethanol to ethanoic acid. Write the molecular formula. It's a bit of just an extension question. So C2H6O No. Let's try it out. Bonus question for those who've finished. The ethanol is C2H6O, goes to ethanoic acid, which is C2H4O2. Can you balance that half equation as well? You finished it? You can have a go at the bonus question then, which is the half equation for the oxidation reaction. You lucky thing seeing extra questions. Right, he's hiding back there. I can't see it behind there. It's coming your way, Rohi. Come on, let's have a go at balancing this top one while some people are finishing off the other one. So, how many chromiums on the right? Yeah. How many? What do we add next? Yeah. How many and where? Then what? H2 or something else? H plus. Then? Well done, on the left, 6 electrons on the left, right? You put the electrons, so you get the charges the same on both sides. So this side is now plus 6 and the right side's plus 6. It was plus 12, so I added 6 electrons to the more positive side, yeah? Now, this, folks, is a really important point that is missed easily if you're not paying attention right now. So people often ask, well, why have I got to chuck acid in there? What's the purpose of the acid? I got this exact question after teaching this. I think it was from Louis last time. So, you know, very good student, not spotting the purpose of the acid. The acid is there because you can't reduce dichromate without acid, because to reduce dichromate you need H plus to make the water. To pull those oxygens off the dichromate you need the hydrogen ions. So the hydrogen ions are given to the equation by chucking in sulfuric acid, the source of that H plus to make this equation work. Right, is that clear? Important point. If you manage to do the other equation, I'll just do it quickly for you. I think it's water there, and then 1, 2, 3, 4, 5, 6, 7, 8. So we need 8. That's wrong, isn't it? 1, 2, 3, 4, 6, 8. I'm an idiot. There's 4 H plus and then 4 electrons. Sorry, I've rushed that. I hope it's right. Okay, so that's the other half equation that's going on. 4 H plus and 4 E. That's a mess. Right, okay, so let's do a little bit of thinking then. By the way, this reaction, you see it going from orange to green if it's working. If you've not got an excess of this stuff, you can see the green forming quite quickly, actually. Quiz question then. And draw them again. I'm going to ask you, and I'll start drawing them so we can talk about it, but of those 3 molecules, the ethanol, the ethanal, remember the name? Ethanal, because it's an aldehyde, alpha aldehyde, and the ethanoic acid, which has got a carboxyl group on it. I want an order of boiling point, which is the lowest boiling point, which is the highest boiling point, and an explanation. Discuss. Tom's bored. He's on his smartphone, so I'll do. It's good enough for me. Tom's had enough, so he's calling it. It's calling it to a halt. So tell me, Tom. Ethanol's the lowest. Is that what you said? Then ethanal. Then the ethanoic acid. And your justification for that? Right, it sounds to me, Tom, like you think that when something boils, the bonds break. You just told me that when you break, when the molecule is boiling, the bonds are breaking, right? But I think you know, don't you, that when you boil water, I think you know, don't you, when you boil water, the bonds don't break. When you boil water, it doesn't turn into hydrogen atoms and oxygen atoms, does it? That would be embarrassing. Imagine if you did that and you destroyed the world, okay? That's no good. What is it that actually is breaking when you boil water? What are these little dotted lines called that I've drawn here? Right, so I think we need to rethink your answer. We've got to think about which have got the strongest intermolecular forces and why. So I'm going to go back to Zara to take Tom's answer, point and laugh at Tom a little bit, and then tell us your answer, make it better than his.
I'm good. Sorry. I think the one person to the right is just got the highest boiling point.
Okay.
And then followed by close to the left, and then the middle's got the lowest one.
Why?
Because they can make hydrogen bonds.
That, I don't know which one you're talking about.
The one on the right.
So this can make hydrogen bonds.
Yeah, and so it's on the left, I think. Because there's a hydrogen bond donor and...
This one can make hydrogen bonds, is that what you're saying? How about we use words? This is ethanol, ethanal, ethanoic acid. So ethanoic acid can make hydrogen bonds, and ethanol can make hydrogen bonds. Because it's got a hydrogen bond donor and a hydrogen bond acceptor.
Yeah.
Go on, keep going.
And ethanol can't, because it hasn't got hydrogen bond donor, hydrogen bond acceptor.
It's got a hydrogen bond acceptor,
Oh.
but it hasn't got a hydrogen bond donor.
Yeah.
Yeah, so it can make hydrogen bonds with other things, like water. So it's why it's slightly soluble in water. But it can't make hydrogen bonds with itself. That's right. So, don't forget though, when you were explaining this in the exam, so that's fantastic by the way, really good. But I'm expecting you also to say they can all make dipole-dipole interactions, and they can all make London force interactions. Is that right? They can all make dipole-dipole interactions, Scarlett? I've already asked you a question, haven't I? If I not asked a question, Lewis, is it right they can all make dipole-dipole interactions? Okay, talk me through that. How do you know? How do you know whether? How do you know whether things can make dipole-dipole interactions? That's really what I want to know. So talk to each other and I'll listen in. So what I've just pointed out to you is that all the molecules make dipole-dipole interactions because the carbons are delta plus and the oxygens are delta minus, and the hydrogens are delta plus if they've got a hydrogen next to an oxygen, okay? And that's because of differences in electronegativity between those atoms. The follow-up question I've got, which I'm going to pause the video for to spare the people listening, is why is oxygen more electronegative than carbon? The electrons in these bonds are being pulled both directions by the nuclei there. The oxygen and the carbon are roughly the same size. Oxygen's slightly smaller, but not much. But it's got 2 more protons than carbon. Okay, so those electrons are pulled slightly more towards oxygen than carbon. Does that ring a bell from earlier in the year? It's really important you can still do this stuff. Really, really important. So the point is that the aldehyde has got a much lower boiling point than the others. This actually has got the highest boiling point. I don't know how you differentiated between the... Who's got the right answer? I can't remember who it was. Doesn't really matter. But whoever it was, they said this has got the highest boiling point. Hard to differentiate between those two. Why do you think this has got a higher boiling point than this one? People? Anyone? Hands up. Gregor? I think that's a marginal difference. I think it is part of it, but it's a much bigger difference than that would account for. Greater permanent dipole would certainly be true, but also it's got 2 sets of hydrogen bond acceptors, 4 lone pairs, if you like, that can grab onto a hydrogen on a neighbouring molecule. So that's an effect. Actually, what happens in reality is they kind of form this weird dimer. So you can imagine 2 ethanoic acids, one of them flipped over, and they kind of hang out with each other, making this sort of ultra big. Anyway, sharp. So yeah, it's got a fairly high boiling point. The key thing that you need to know though is that this has got a low boiling point, and that's important because it might be we want to turn the alcohol, primary alcohol, into an aldehyde, but stop it there and not turn it into the carboxylic acid. Aldehydes are extremely easy to oxidize. How many of you here did biology? How many of you here did biology at GCSE and learnt about the the test for sugars. You did learn the test for sugars? What's it called? Is it Benedict's or Failing's use? Benedict's. So that blue copper sulfate, don't you? That's an oxidizing agent. Sugars, when they react, they form. When they in their sort of open form, they have aldehydes on them, and the aldehydes are being oxidized even by copper 2. The copper 2 turns into copper 1, and that's what's going on. So aldehydes are very easy to oxidize, even with something as simple as copper 2 plus, right? So aldehydes are very easy to oxidize. So how do we get the aldehyde out of the pot when doing this reaction? And what we do is so alcohol, so primary alcohol to aldehyde, we heat and we do it under distillative conditions, but we heat and distill at the same time. So heat and distill the product as it's forming. So what we do is we do a setup like this, and by the way, I'm expecting you to be able to reproduce even a crummy diagram like this one. It doesn't have to be neat or look good, it just has to kind of function as a diagram. So I've got a reaction going on, and I'm setting this up for the other group later this week. And if you want to come along on Wednesday lunchtime to see the setup, you can do. I'll do it with you at the start of the new year. I don't see you enough to make this actually happen in class for you guys in the short term. If you're desperate to see the setup this side of of summer, do come and see me at Wednesday lunchtime when they're going to have it set up. But this is a terrible picture, but you get the idea. So we're heating a flask which has got our reactants in it, including the oxidizing agent, and I've got a thermometer here. I'm heating it probably in a water bath, and I've got a condenser where I've got water pumping in from the bottom and out at the top. Okay, that's going to cool down the vapors, and I'm going to collect the distillate, which is the aldehyde, over here. So do you want to sketch that, then I'll walk you through what's going on. RCHO is aldehyde, if you're not sure. Shorthand for aldehyde. I will share a video of this if you want to look at it earlier as well, because I've got a video that I can show you too. But I'll try and do it with you in the new year. Alright, so what's happening in there is you've got the alcohol and the acid. You heat them up, they react, they form the aldehyde. The aldehyde's got a very much lower boiling point than the ethanol. Ethanol's got a boiling point of around 70 to 80 degrees C, and the ethanoic acid's about 119, I think. And this is way lower, like 40 odd degrees. So the ethanol immediately, very easily boils, evaporates, if you like, at that temperature, and fills this area as a vapor. It's no longer touching the water or the oxidizing agent that it's in there with. So it can't be further oxidized. It comes around the corner because it's going as a vapor, and it gets cooled down. The water cools it down, it turns into a liquid and drips into here. Okay, so we end up with the aldehyde forming over there. So hopefully you've got the idea. Does that make sense? I've often explained this and it makes sense to me, but does it make sense to you? I'll go through it again. Look at everything in there. We've got the alcohol, we've got the oxidizing agent, the acid, a bit of water to hold it all in solution, heating it probably about 50-60 degrees. As soon as the aldehyde forms, it boils because it's got a boiling point higher than that, lower than that of the solution. Jumps out, if you like, and then fills this chamber with the vapor. Vapor comes around the corner, gets cooled down, turns back into a liquid, and down here. Give me a little thumbs up if that kind of makes sense to you. You can kind of explain that because it's got a lower boiling point than the others. Right, so how about if you wanted to go straight to, oh, by the way, let's add a little detail here. No, let's get that. Primary alcohol to carboxylic acid. That says primary alcohol, sorry you can't read it, to carboxylic acid. Primary alcohol to carboxylic acid, and this exact same method works for secondary alcohol to ketone. The same thing. Right, what you do here is you do a process called heat under reflux. Heat under reflux. You need to know that exact expression, those exact words. If you say reflux it, which is what chemists, you talk to any chemist, they'll say, oh, I refluxed it for an hour. If you say that in an exam, you don't get the mark. It's not a verb. You heat under reflux. What that means is you heat it in a setup that looks a bit like this. So we've got, again, a flask. Could be a round bottom flask. It probably would be, actually. I've done it as a pear-shaped flask, but a round bottom flask. There you go, there's a round bottom flask like that. And we've got reactants in there, so that's the alcohol. And it's the carboxylic acid, so it's the alcohol, it's the oxidizing agent, it's the acid, all in a pot together, and you heat that up. But this time you have the condenser vertical. Still with the water in at the bottom and the external jacket. You know how a condenser works. You've all seen a condenser probably in lower years, haven't you? With a water jacket around the outside, lots of nods around the room. Water out at the top. This has got to be open at the top. Otherwise we'll get a nice... Hello Freddie. I'm recording everything, by the way, so you can watch the entire lesson at your leisure, okay? How did your thing go? Good, that's it. So, so you just take it easy for the next bit, okay? Because you can catch it later. So we heat it up. Now this time, I'll give you a chance to just copy the diagram, then I'll walk you through what's going on. You know these if you want them. You might want to write out your own version of them. I mean. Okay, so what's happening here is exactly the same as before. So we've got the primary alcohol and the acid and the oxidizing agent in the pot. An aldehyde will form. Aldehyde's got a lower boiling point. Why has it got a lower boiling point? Does it make hydrogen bonds or not? No, it doesn't make hydrogen bonds. It's got a lower boiling point, it can make hydrogen bonds. So it will boil, turn into a vapor, travel up here. It's going to cool down as it hits the condenser. What's going to happen to it then, Lewis? When it hits the condenser, it's going to condense, well done. And so it turns back into a liquid. It's going to run back down, drop back into the pot again. It's going to keep doing that for a bit. And eventually, though, there'll be enough of it in solution and it will hit the oxidizing agent and it will be further oxidized up to the carboxylic acid. So you go directly all the way from the primary alcohol. Just like I've written this on a previous page, but we doubly oxidize it, so I should put a 2 there, all the way to the carboxylic acid. Okay, so that reaction does do that in one sort of physical step. It happens in 2 steps, actually in the pot, if you like, but we effectively see it as one step. Now, to extract the carboxylic acid out of the reaction mixture or the ketone from the reaction mixture, we then might perform a distillation by distilling what's in here to try to distill the product out, but that's a different process, one that you don't need to worry about. We'll do that reaction for real. If it works with the other group on Wednesday next week, I'll do it with you guys next year. We'll have a go at it and we can prove we made the carboxylic acid by smelling it. It will smell like vinegar. Chuck a bit of magnesium in it, just like you've done with Mr. Craig recently. It should fizz quite gently. We can maybe test the pH and all that kind of stuff, right? I don't think I want to do anything else with you today. I think we've got about 5 minutes, so I'm going to use, I think it's a good place it's a tidy place to stop. I've got a bit, yeah, I mean, I'm happy with where I'm at, so I'm going to stop it there and we're going to do a little bit of practice for the last 3 or 4 minutes before we pack away, okay?